Welcome all of you. So previously we studied solar cell characteristics, the PV and IV curves, how we can connect them in series and parallel to get the desired power at desired voltage. And then we looked at different components of solar PV system. And continuing with that, in today's lecture, what we'll look at is different types of PV systems, how we can classify them, whether they are connected on grid or not connected to the grid. Then we'll focus mainly on standalone PV system, explaining or studying all the components which are the part of that PV system. And finally, we'll look at how to design a standalone PV system. So types of PV systems, they would be classified based on multiple factors. Most important of them are the availability of the grid. If grid is available, it can be grid connected system. If grid is not there, it can be off grid system. Intended application, for what purpose that PV system is going to be used, whether it is going to be used to supply electricity to houses or for powering solar pumps in agriculture or powering an industry, and the need for backup power, whether we need a battery or we don't need a battery. So based on these three factors, solar PV systems are classified in three broad types. One is standalone PV system, hybrid PV system and grid PV system. Standalone PV system, they can come without battery or with battery. They are the ones which are independent and they do not need grid, but often they will require the batteries, because when sun is not present, like say at cloudy days or at night, to keep the appliances running, the off-grid or standalone PV system will often need batteries. But there may be some cases of standalone PV systems which are there without batteries, where a load like a street light or a lamp is directly connected to a PV system without any battery. And when it comes with battery, it can power both DC and AC systems. We can have a converter or inverter which can supply power to both types of loads. So that's a standalone PV system. Second, grid connected PV system. So in this, these are mainly direct utility connection that offsets bills via net metering, and it shuts down during the blackouts, because those PV systems are connected to the grid. If grid shuts down, the PV system will also shut down because meter will not work. So grid connected PV system are of two types. One is bimodal PV system, where we combine the benefits of both standalone and grid connected PV system, because in this case, even though they are connected to the grid, we will have a separate storage system, that is separate battery system to supply power when grid shuts down. And the one which are directly connected to utility or grid, they will be typically without battery system. So if grid fails, the PV system also fails. Third one is hybrid PV system. There are two ways to look at how hybrid PV systems are defined. If you look it from the point of perspective of grid, these are the one which are connected to the grid with a battery reserve or connected to other energy source. And as you can see in the picture, this shows where solar PV is connected with some other renewable or non-renewable source of energy. For example, it can be connected with wind turbines or hydro turbines, a diesel generator or a fuel cell or other sources. So two different sources integrated together to provide power. So those are called as hybrid PV systems. Other definition would be, it is connected to the grid as well as it is connected to a battery reserve or to some another energy source. Those are the three types of PV systems. If we compare them on the basis of different features, we get this table where grid connection is required, no. For grid tied, yes. For hybrid, yes, it is required. Battery storage, off grid, it's required based on the load, AC or DC. Grid tied, it is optional or it is rare. Most binaural systems won't be used often, mostly directly connected to utility type of systems would be used. Hybrid, it is required. Backup power, yes, there is a backup power, battery is there. Grid tied will often no, and hybrid there will be a battery to supply backup power. Cost, it's highest mainly because of batteries, lowest, and then moderate to high. Complexity is high because of more number of components in a standalone PV system. Then in grid tied, no, low cost, and hybrid the cost would be moderate. In addition to these three types of PV systems, there are some specialized PV system configurations that you may be encountering in the recent years. One is building integrated photovoltaics. So, the walls of the buildings or the glass panels of the building can be in PV based. So, PV are actually integrated with the building materials, and most of the time it's thin film amorphous type of silicon cells which will be used because of the curved nature of the buildings. Concentrated PV, where we would be using lots of mirrors to concentrate or reflect solar energy into a receiving PV panel. Floating PV, one of the concerns for solar PV plant is obviously low efficiency, but huge land area which is required to generate 1 unit electricity power. So, if PV can be installed on the water bodies like say lakes, ponds or seas or oceans, and sometimes huge wastewater treatment plants. So, it can provide some benefits of like say reduced water evaporation, and they may also have some cooling effect on the solar PV panels during the times of extreme heat and summer. And if it is PV panels are to be cleaned, then there is a readily a source of water available. So, floating PV are a new field coming in the picture. Then agrivoltaics. If we could use agricultural land for installing solar PV panels, but then studies are going on to find out what type of crops can be grown, what would be the inclination of panels, what would be the distance of two panels, how the concrete structure would be installed without affecting the growth of crops or agriculture. So, these are some specialized PV system configurations in addition to these three types of classification based on grid availability and backup power. Now, coming to standalone PV system. So, it is also known as off-grid system. It operates independently of the electrical utility grid. Since it can generate and store energy, it is best suited for remote areas, rural electrification, or in the areas where there is a need for emergency backup power. If you look at the picture, you can see these are the major components of standalone PV system. So, to capture sunlight, we need solar PV panels, which can be placed in the form of arrays. Then, solar PV panels would generate DC power, and that DC power has to be converted to AC, for which we will need a inverter. But between solar PV panel and inverter, there is a charge controller and a battery bank. Charge controller is to ensure the batteries do not get overcharged or do not get discharged beyond its capacity. So, it acts as a protecting device for battery bank, and off-grid inverter, charge controller, battery bank, as well as solar PV panels, all of them would be kept possibly at the similar voltage level to reduce the losses. So, these components can be defined one by one. PV modules, it is a primary energy source that converts light into electric current. Charge controller, it is a voltage and or a current regulator which is protecting batteries from overcharging or over discharging. Battery bank, it is used to store the excess energy which is produced during the day, and that energy can be used at a time when there is no sun, preferably at night or during the cloudy periods. The fourth component was inverter. Inverters will convert the DC power obtained from solar array, which will be typically in the range of 12 volt, 24 volt or 48 volt, and convert this DC power from solar array and batteries into AC power of either 120 volt or 240 volt, because that is the voltage at which Indian residential houses use the power. Then finally the AC and DC loads. These are the electronic devices like lamps, motors, which actually consume the generated power. So when we design, we'll go from bottom to top. First we know the load, and accordingly we can design the previous components and stopping at PV module. Like I said earlier, to minimize the losses, the voltages of all these three equipments like battery bank, PV array and inverter, they are kept nearly at equal value. We can have voltages of equipments different, but then it will add more number of electronics such as step down or step up voltage or transformers, which will add to the cost of the system. And to minimize the cost and to minimize losses, it is preferred that all of these components are operating at same voltage. So before going to the step-by-step design of standalone PV plant, for battery bank there are different terminologies related to battery which we are going to use in the design. So let's discuss them first and then we'll go to the design part. So efficiency of battery or efficiency of any electrical equipment would be energy output by energy input. Depth of discharge. So if you take example of a lead acid battery, you might have seen that you keep on filling the liquid, some water like liquid, every 2 months or 3 months when the battery is not working fine. Okay, so those kind of batteries or any battery like even lithium ion battery, they can be discharged to a certain point to maintain the health of the battery. So depth of discharge represents the percentage of total battery capacity that has been or that can be used related to overall capacity. So 100% DOD means we can drain the battery completely, and if it is 50% DOD, we can drain battery to only 50% of its capacity. For lithium ion batteries, the number is high, it is 80 to 90%. Next point is autonomy. Autonomy, it refers to the number of consecutive days a standalone system can meet the load without any energy input from solar array. For example, if we want to design a battery system for 3 days, autonomy is let's say 2, then we will be designing a battery system that can hold the charge storage for 3 days. Okay, so if autonomy is 3, charge storage will be for 3 plus 1, 4 days, because 1 day would be for today and 3 plus extra days with no sun. So for a typical region, if we know that sun won't be available for 2-3 days or 4 days, accordingly autonomy can be decided and the battery backup system can be designed accordingly. So now coming to the solar PV, standalone solar PV system design. If you go step by step, the first step would be determine the power load. What is the demand? Whether it's AC or DC, what is the total power load or demand? It will be calculated using simple formula. Daily energy consumed would be the rating of the equipment, that is watts, into usage per day. Second, determine the size of inverter. For this, you will have to assume that all the equipments that are there in the load are on, and what would be the rating of each of those equipment and the total power rating, whether that much is able to be satisfied by the inverter. Based on that, inverter size would be determined. Determine the size of battery bank. When you define a battery bank or design a battery bank, you take into account depth of discharge, autonomy and the arrangement, because batteries can be connected in series or parallel for addition of voltage or current or the total power. Determine the size of power controller. This will depend purely on the efficiency of the power controller. The last would be find or determine the size of PV module or array. It will be based on solar radiation data for a given region. And since PV modules can also be connected in series or parallel, we have to give the arrangement. From step 2 to step 5, efficiency of each component must be considered when we determine what is the energy input to that particular component. Okay. For PV module rating, if we know the PV module output, that is the peak power output and peak sun hours per day, we can find the PV module rating. Peak sun hours, if it is not given directly, we can calculate it from the given solar radiation. For example, if solar radiation is say 5000 watt hour, so we will divide it by 1000 kilowatt. The standard radiation, I think it's in watt. Okay, so it will give us 5 hours of peak sun radiation. So based on overall solar radiation, we can calculate the approximate peak sun hours per day. Let's take one numerical example to understand how we can design a solar PV system in a standalone mode for a given load. This is a question. Design a standalone PV system for following load of a small house in Roorkee, where radiation is 6000 watt hour per meter square, latitude is 30 degree north. These are the items: TV, fans and light, 1, 2, 3, and ratings of each equipment are given, and these are the usage. This is the given data, and we know the components of standalone PV system, and all those components will be purchased from the market. So some market availability ratings would be given to us. For example, inverter, it's 90% efficiency, battery 24 volt, depth of discharge 50%, efficiency is 80%, autonomy is 2, and the ones which are available in the market are of 12 volt 100 ampere hour. Charge controller efficiency is 95%, PV modules 24 watt, and the one available in market are 60 peak watt and 12 volt. Right. So this is our given numerical with the data. Now let's solve the problem. In solution, first step would be determining the power load or the demand. That's the first step. So that table is given to us. Based on that table, we can find total load. There was one TV of 100 watt, usage is 2 hours per day. So total usage would be 100 into 2, it is 200. For 2 fans, it will be 2 into 50 into 8, it is 800. And for 4 lights, 4 into 10 into 5, 200. So if we add these watt hours per day, this is 1200 watt hour per day, that is the power load. Okay. Once we know the power load, second step is determining the size of inverter. For size of inverter, we assume that each of these appliances are switched on simultaneously. So the maximum wattage that we would require would be 1 into 100 plus 2 into 50 plus 4 into 10. So it will be 100 plus 100 plus 40. So almost 240. So the total power that is needed to be supplied from the inverter would be 240 watt or 240 volt ampere. Okay, that's the second step, where we have determined the voltage or the wattage of the inverter, that is 240 watt inverter. It may be available in the market. Now the efficiency of inverter was given to us 90%, or so energy output of the inverter has to be 1200 watt hours, and since efficiency is 90%, the energy input to inverter would be 1200 by 90% of it, 0.9, that is 1333 watt hour per day. We can also write it as volt ampere hour per day. That's the second step. First, we calculated the total power load. Second step, we found the rating of the inverter and energy input to the inverter, right? Now, third step is determining the size of battery bank. In battery bank, there are a lot of things coming. In addition to efficiency, there is depth of discharge, autonomy, and the configuration, right? So the given voltage for the system in numerical was 24 volt. So it is the battery system which should supply the energy given by the inverter at this voltage. So battery should supply 1333 by 24, that is 55 ampere hour per day. That is the need from the battery. So the battery system capacity to be able to supply this much, if we take into account depth of discharge, the battery system capacity should be much bigger than this, that is 55 by 0.5, that is 111. Now this is the battery system capacity considering only the DOD. If we account for autonomy, which was 2, so charge storage would be for 3 days, because we add 1, that is for the today, into the number of days in the autonomy. So for 3 days, battery system charge capacity would be 111 into 3, 333 ampere hour. Now in the market, what is the rating of the battery? It is 12 volt and 100 ampere hour. Now our requirement is 333 ampere hour. So the total number of batteries based on ampere hour would be 4, because we cannot have 0.3 batteries. So we will just round it off to a next even number, that is 4 batteries. And energy input to battery would depend on the efficiency of the battery bank, that is 80%. So 133, this is what battery has to supply, and battery has to supply to the inverter, okay, because this is the energy input going to the inverter, right. So here is the battery, here is the inverter, and here is the load. So load is 1200, inverter is receiving 1333 and giving 1200 because of its efficiency of 90%. Now battery has to receive much more than this based on its efficiency of 80%, which is 1667. So out of 1667, it is giving this much to inverter, and then out of this much load is 1200. It depends on the efficiency of inverter, efficiency of the battery. Now before battery there will be the charge controller, okay, it will depend on the efficiency of charge controller, like what is the number here. Now so we have calculated that what we need is 4 batteries and energy input to battery is 1667. But now with these 4 batteries, how are we able to get a 24 volt system? Because each of these batteries are 12 volt. So obviously if we connect 2 batteries in series, the voltage would be V1 plus V2, that is 24 volt, and then those 2 strings can be connected in parallel, something like this. So B1 and B2 are in series, B3, B4 are in series, and these 2 strings are connected in parallel to each other. So the voltage here would be added up, that is 24 volt, 24 volt, 2 strings in parallel would be 24, and this ampere hour addition would be just B1 plus B2 plus B3 plus B4, it is 400 ampere hour. So this is how the arrangement or configuration of battery bank would look like. We will have 4 batteries of 12 volt each, 100 ampere hour each, but this is how we can arrange them to obtain a 24 volt 400 ampere hour system, okay. That is the third step, battery bank. Now energy input to battery is 1667. So this is basically the energy output from charge controller. So fourth step would be determining the size of power controller or charge controller based on the efficiency of charge controller. So energy input would be 1667 by 95.95. So 1754 watt hour per day is the energy input to power controller. And what is giving energy to power controller? PV module, right. So PV module gives power to power controller, then battery, then inverter, and then the load. So and PV module rating would depend on the radiation of the given region. So Roorkee radiation is 6 kilowatt hour per meter square day. So peak sun hours would be, if we divide it by 1000, it will be 6 hours. So that's the peak sun hours. and the PV module rating would be total energy input upon peak sun hours. This is 1754. This is going to be fed to the power controller. So, this is going to be the output from PV panel. So, this PV panel output or PV module output of 1754 upon peak sun hours gives us a PV module rating, which is coming out to be 292 peak watt. Now, in market, one PV module is of 60 watt and voltage is 12 volt. So, here also we need a system of 24 volt, but before that we will calculate the number of PV modules by dividing 292 by 60. So, that comes out to be 4.87, approximately 5 modules. Now, 5 modules of 60 peak watt and 12 volt. It will be difficult to connect them in series and parallel to obtain 24 volt system. So, to avoid that situation, the thumb rule is just round it off to the next even number. Okay, so after 5, next even number is 6. So, if we have 6 modules, then we can have 2 modules in series to get 24 volt and then 3 strings of those 2 modules in parallel. Okay, so P1, P2 in series. So, this is 12 volt, 12 volt. So, it is added to 24 volt. This will be 24, this will be 24. So, when they are connected in parallel, voltage is going to stay fixed. Current is going to get added up. So, power is going to get multiplied, that is 60 into 6, 360 peak watt. And this is how the PV module system would be arranged. So, we need 6 modules for 24 volt system. We would be arranging them in this pattern. So, this sort of completes the design of standalone solar PV system. So, how we started? We started from the load, the total energy requirement. Then, assuming all the equipments are on, we determine the size of the inverter. Based on the efficiency of the inverter, we determine the battery energy input, and then in battery we had a configuration like this, which was based on depth of discharge, autonomy and the required system voltage. Then we designed power controller based on its efficiency, and finally PV module based on the peak sun hours and radiation data and how we can arrange them to get required system voltage in series and parallel. Okay. So, that completes the design of a standalone PV system. To summarize, so what we covered in today's lecture was different types of PV systems, mainly 3 types based on availability of grid and the backup power and its intended application. So, what were the 3 types? Standalone or off-grid systems, grid connected systems and hybrid systems. Then we focused mainly on standalone PV systems, where we looked at 5 components of that system, and then there was a design of that PV system where we followed bottom to top approach, starting from load and going all the way to design of solar PV module or the array. Then we looked at one numerical to explain how we can design the real world solar PV system for a small house. So, with that, let's close the lecture today. Thank you.